Good day everyone. In this video, I'll be going to perform the Laboratory 4 entitled Comprehensive Performance Analysis of Various CMOS Logic Families using 3-input source circuit under different loading and frequencies. Here are the objectives in this laboratory. First is to analyze the performance of 3 different CMOS logic families, static CMOS, pseudo-NMOS, and pass transistor, by evaluating power consumption, propagation delay, and power delay product using 3-input source circuit as the basis for comparison. Second is to investigate the impact of varying capacitive loadings in the circuit's performance, specifically in terms of delay and power consumption, and to determine how different logic families respond to these variations. Last is to examine the effects of increasing input signal frequencies on the circuit performance under a fixed loading condition, assessing the resulting changes in power consumption and delay across the 3 logic families. Using the 45 nanometer technology of cadence BATAUSA, the student followed the schematic diagram given in the manual of the static CMOS. The transistor length of both PMOS and NMOS is 0.18 micrometer, while the width of the PMOS is 6 micro and the width of the NMOS is 3 micro. In the inverter side, the size of the width of the PMOS is 2 micro and the size of the NMOS width is 1 micro. Here is the final schematic diagram of the static CMOS. After that, the student launched the EDEL to plot the wire of both the inputs and the output. And the student used transient analysis to sweep the waveforms to 640 nanoseconds. To measure the propagation delay, the student sent the waveform of the input into the calculator as well as the output waveform of the output. Then the student used the delay function. So the input is sent to signal 1, then the output is sent to signal 2. Then the threshold voltage is 0.9 volts and the edge type is 1. To measure the power consumption of the circuit, the student plotted the supply current waveform and it was sent to the calculator and used the function average and multiply the expression to 1.8 volt. Lastly, to measure the power delay product, the student simply multiply the delay and the power consumption to measure the PDP. To perform the parametric analysis, the student make the capacitance loading as variable C, and it was swept from 0.05 pico to 0.5 pico to visualize the power consumption and delay in these values of the capacitors. When the rectangular plot was shown, the student also performed or converted into tabular to see the numerical values behind this capacitance loading. Additionally, to test the static CMOS circuit, the student modified the input pattern while maintaining a fixed loading capacitance of 0.05 picofarad. The input signal frequency was increased by factors 2 times, 4 times, 8 times, and lastly 2 times, requiring adjustment to the signal period and pulse width accordingly. Since the frequency and period are inversely related by the formula period equals to 1 over frequency, the period for each case was divided by the respective frequency multiplier. As a result, the pulse width was also adjusted proportionally to maintain the same duty cycle. The results in Table 1 showed the propagation delay remained constant at 273.16 picoseconds regardless of the frequency multiplier. This indicates that the circuit delay is dependent on input signal frequency. However, power consumption increases proportionally with frequency, and the student also observed there is a huge difference between the values of each frequency. Now we move on to the pseudo-INMOS 3-input source circuit. The student simply followed the circuit shown in the manual of the pseudo-INMOS 3-input source circuit. The transistor sizing was set with a W/L ratio of 1 micrometer over 0.18 micrometer for NMOS and 2 micrometer over 0.118 micrometer for PMOS to balance performance and power consumption. Here is the final schematic diagram of pseudo-INMOS 3-input. The test bench setup followed a similar approach as in the static CMOS experiment. The input signal were generated using pulsars with a voltage swings of 1.8 volts, a rise and fall time of 0.1 nanosecond, and varying period according to the test conditions. The output was loaded with a fixed capacitance of 0.05 picofarad, and threshold analysis was conducted over 640 nanosecond simulation time. To measure the propagation delay, power consumption, and power delay product, the student followed the same process happened in experiment 1 in the static CMOS. The student also followed the same process in modifying the input pattern while maintaining a fixed loading capacitance of 0.05 picofarad. The input signal frequency was increased by factors 2 times, 4 times, 8 times, and 16 times. Here is the summarized table in varying the input pattern of the pseudo-INMOS circuit. Last experiment is the pass transistor 3-input source circuit. The student followed the same process, following the schematic diagram of pass transistor 3-input based in the manual. This circuit utilized NMOS transistors to selectively pass logic levels, reducing the number of required transistors compared to conventional CMOS logic. The transistor sizing was set to W/L 1 micrometer over 0.18 micrometer for NMOS devices, ensuring proper signal transmission while maintaining low power consumption. Here is the final schematic diagram of pass transistor 3-input source circuit. To measure the propagation delay, power consumption, and power delay product, the student again uses the same process what he did during the first 2 experiments. The waveforms were sent to the calculator, and to measure the propagation delay, the student used the function delay, while to perform a power consumption measurement, the student uses the average and multiply it to 1.8 volts. And to measure the power delay product, the student just simply multiply both power consumption and propagation delay. The student is now performing the effect of frequency scaling. The inputs were modified to operate 2 times, 4 times, 8 times, and 16 times the original frequency while maintaining a fixed load capacitance of 0.05 picofarad. Here is the summarized table of propagation delay and power consumption of bus transistor, a 3-input circuit at varying frequencies. After this laboratory 4, the student concluded that it was observed that the larger capacitances lead to higher propagation delays and power dissipation. The results demonstrated that propagation delay remained nearly constant across frequency changes, whereas power consumption increased proportionally with frequency. Overall, static CMOS emerged as the most energy efficient and noise-immune logic family, making it suitable for low-power applications. Pseudo-in was provided faster switching speeds and reduced transistor count but suffered from static power dissipation, making it ideal for high-speed, less power-sensitive design. Last is the pass transistor logic. While requiring fewer transistors, it faced challenges related to signal degradation and voltage loss, limiting its application in low voltage and high-speed circuits. This has been Angel T. BATAUSA, and thank you for watching.